This is Frank. Frank changed the RTL for one field in one register, and he didn't tell anybody. That caused the software on the chip to stop working, which caused the drone it was controlling to crash into the home of someone who got a bit irritated. We interrupt this commercial to bring you this important message. It has come to our attention that many design teams suffer from non-automatitis or scriptophobia. These have been known to cause headaches and respin regurgitation. If you experience these symptoms, contact Semaphore for a no-obligation checkup. You don't have to suffer. Reach out to Semaphore. We now return to your regularly scheduled commercial.
Hi, welcome everybody. My name is David Rich, and I'm the chair of this session on regression, runtime, and debug optimization. And I am a verification technologist at Siemens EDA. I've been working on system Verilog, and test bench methodologies for many years. Today's session is on dealing with the vast amounts of data generated by running regressions and how we can improve the performance, improve the coverage results, and improve getting to coverage closer much faster. Our first speaker today is Ashfaq Khan, and he is an engineer at Intel, and he did his undergrad and master's from Tohoku University in Japan, and he's got a PhD from Boston University. And he's primarily interested in computer engineering with a focus on EDA and simulation technologies. He's worked for multiple semiconductor software companies in the past decade in the USA and Japan. And Ashfaq leads a RTL design methodology and automation tool flow for cutting edge SoCs. And with that, we can start the presentation.
My name is Ashfaq Khan. Welcome to this presentation at DVCon 2022. Now that you know what I look like, let me start sharing my slides and turn the video off. So the title of today's presentation is Caching Tool Run Results in Large-Scale RTL Development Projects. This is the outline of the presentation. I'm sure this is not something you think about every day when you're developing an SoC. So I'll spend a few minutes describing what we mean by caching and why this is important for EDA tools. And we'll also talk about what it means for large-scale projects versus just an individual user or a small team. For this agenda to make sense, I'll just explain that by caching EDA tool run results here, we mean basically reusing the tool run results from one run to another. We'll talk about the challenges that you might face in utilizing any of these caching mechanisms and what you need to consider before you deploy these for your projects. We'll talk about various caching methods and their pros and cons, including one that we are proposing and suggesting here. We'll go into the implementation details of some of them with more focus on the proposed method. Then we'll talk about results from production deployment. And at the end, we will have conclusion. This will include asks from the EDA industry. All right, so let's get started. Why we are talking about caching EDA tool run results. This basically comes from the observation that as your project becomes larger, RTL designers typically start spending most of their time doing a specific section of the design. So 100% of the design changing in every tool run is a very rare scenario. What happens most of the time is that the EDA tool runs that they have, one after another, they typically have most of the design pieces unchanged. A very small portion of the design actually changes from tool run to tool run. So this provides us with a major opportunity for resource optimization. When we're talking about resource, we're talking about compute and human resources. So if we can use caching for EDA tool runs, we are basically reusing the tool-generated content. If we can do that, this will reduce or even in some cases eliminate certain tool runtime. This provides us with the opportunity to save human resources, also to save compute and machine resources. Let's take one example. We'll take one that should be easily relatable for all RTL designers. If you are recompiling a design for simulation, and let's say you change only one line of code, there's no point recompiling the entire design or elaborating the entire design, right? So there are mechanisms to split your design so you don't do that. And then there can be an additional step where you use cached tool run results from previous runs. So only the portion that you actually changed is rerun. So there could be other examples on vendor EDA tools or even in-house developed tools. So that's what we mean by caching EDA tool run results. Now, when you are eliminating some tool runs just by reusing the results, that's one scenario. But if you want to reuse parts of your design, EDA tool run results, then that particular tool also has to support caching. So on the left-hand side, we're assuming we have tools like this. So on the left-hand side, what we're showing is what happens when an individual user runs the tool. You have your design input. At the very initial run, you have a cold miss because there is nothing cached yet. So you run your result, then you get your initial tool run results. For subsequent runs, if your tool is able to reuse some of the results that you had previously, and if your design is not significantly changing, then you should be able to reuse some of these tool results with some design input, and you should be still able to run the tool and generate the desired output. The difference when you come to a team environment is that even for the cold miss that we talked about for the very initial run, you might have somebody or some infrastructure that actually ran this tool already. So you could use that as a shared tool run results even for your very first run. Subsequent runs can continue using that, and it can also use your own run as a designer. So that's where individual run versus team environment comes into play. And as your team becomes larger, that's what we mean by large-scale RTL development. No matter what tool you take, what you want to run, there's very high likelihood that somebody has already run this tool. So it's a matter of finding the tool run results and being able to utilize that. Now, before we can go and start actually using caching in tool runs, you have to consider a couple of things. First of all, if your content itself is reusable, right? It has to be contained. It shouldn't have dependencies on the machine that it was initially run or the collateral that it actually used. It shouldn't have hard-coded paths, stuff like that. So that's the first piece. The second piece is you have to consider the trade-off between saving and restoring, essentially using the caching mechanism, versus regenerating. If your design, for example, is very small and it just takes like a few seconds or maybe a minute to regenerate, then creating that infrastructure and going through this whole exercise of caching might not be as useful. But as your design becomes larger and regeneration takes time, that's when caching will be useful. Then you also have to think about your cache hit rate. So how much of your design is actually changing and how many times you can actually use the cached result. The other piece is that once you decide that this will be useful, you have to have an efficient infrastructure to implement this, right? This will typically involve having a disk, some network access, right? And then ways to store and save and restore. The other piece we want to emphasize is that because these are large-scale designs, you are dealing with billions of transistors. At some point, you want to make sure that the design is fully correct. You are not using some cached content that is stale. So that correctness has to be done at some point. It can be done in many ways, but in this paper, we have focused on having an infrastructure that supports continuous integration. So let's talk about that real quick. So in a continuous integration infrastructure, you have a repository because RTL is text-based. This is easy to do like any other software. So you check out your repository, you configure your IPs if you're dealing with SOCs. You generate collaterals, etc., whatever is needed to get started with your tool runs. Then you change your design or make some updates in how you run the tool. Then you actually run this tool. You iterate for whatever is needed for your activity. Then you submit it to your continuous integration infrastructure. There, that infrastructure should have ways to take input from multiple users, merge it if needed, and then there will be some acceptance checks. Once all those checks pass, the user's submitted changes are made part of the new repository. And then that cycle goes on. So having a continuous integration infrastructure make this correctness issue much simpler because you can assume or you can create that infrastructure such that it doesn't use any cached collateral. So you will have one point where you are certain that you are not using any cached collateral, everything is fresh, and the correctness is guaranteed. User runs, if there is any issue in the quality or correctness, that will be caught in the CI infrastructure. But this can be done in many other ways. You might be able to do it manually or through some other workflow methodology. So in the paper, we talked about infrastructure, CI infrastructure, and how you can build a caching mechanism around that. But it's not a must. There are other ways to do that. With that, let's go to the various caching methods that we have. I've split that into two major categories. One, what we're calling method A, is where you store your cached content as part of the repository. Method 2 is where you store the cached content outside of the repository. So we'll talk about the pros and cons, but this is the major difference in the methods. So this slide, let's talk about method 1, where we store the cached content as part of the repository. So the pro is obviously whatever you cached, it's always part of the repository. So there is no additional effort in restoring this cached content. So in method 1A, we are basically splitting this by who is actually allowed to store this. So in method A, every user is allowed to store. Now, why we are splitting by this category is because when you are talking about tool-generated content and taking them as part of something like continuous integration or merging them together, tool-generated content are typically very difficult to merge. So if you take tool-generated content from every user and try to put that in a repo, it becomes very, very difficult. So that's part of the con, like that's number 2. Like when contents are being merged, it's very difficult. To work around this, the other method could be the storing can be done only by designated users. So beyond those users, the rest of the folks will not touch anything that can change the cached content. The third method would be that CI infrastructure itself will take care of the caching content. So among these three, if we talk about the cons, first con is that all of them are storing stuff inside the repo. So if you have very large cached content or binary content, those don't work well. So that's a common cons for all of these methods. The first method, it's very difficult to make it work because of the content merging issue. 1B, the issue is that now you're restricting what your designers can and cannot do. So it's a very restrictive work model. Third one, if you go with this method 1, third one is probably the most efficient one. But this implementation of this is a little bit complicated. You have to make sure that your CI is able to create those caches on the fly, and that when users check those out, these repos, and they want to see what they need to check in, those cached content don't show up in their search. So there's a little bit of implementation complexity there, but if you want to go with method 1, this is probably the most recommended method. Method 2, on the other hand, stores the content in a separate location. Basically, what this means is that this allows you to copy whatever you want in a separate disk. Right. So that's the pros, right? That's part of the pro is that it scales to any type of collateral or any size, right? Both 2 and B. The other pro is that it's because it's not part of the repository, you can also store like however you want, whatever you want, the length of time. And so management is a little bit easier, right? Work model doesn't change as we saw in 1A. The difference between 2A and 2B is how you retrieve your cached content. 2A, basically we have an automation that will look at your design collateral, see if anything changed, and only then it will retrieve. So that's automatic. In method 2B, we are leaving that decision up to the user. Right. So from our experience, we have seen that users have pretty good idea of what's changing. So we leave that to 2B. And the difference it makes is that implementing these methods, we'll talk about this soon, 2A becomes really complicated. So that's the pro of 2B. It's very simple to implement, and as a result, it's also very easy to maintain. So let's talk a little bit about the implementation details of method 1 and 2A, and the next slide we'll talk about 2B. So method 1 and B, users save the content manually. So if it's a repository, you just check in to your repository and then you submit to your CI infrastructure. In method 1C, as we just talked about, CI infrastructure itself is involved in the saving. So it deletes any cached content first. It doesn't attempt to merge because, like we said, tool-generated content is generally very difficult to auto-merge. So it deletes and then adds and then saves it. Then any cached content is excluded from consideration when a user looks for changes that they need to check in. So that's where you need to do some additional implementation. So that comes as one of the cons of method 1C. But again, if you're going to save in the repo, this is probably the most efficient way to do it. Method 2A, retrieval is decided by checking if the input collaterals actually changed. So this means before we do the caching, you have to look at all the inputs, and the way we implemented this is you can look at your input files, you can create a checksum, and together with the cached content, you save this checksum also. Now, when it comes to retrieval, you'll do something similar. You will look at the inputs, you create a checksum, and then you will check whether for this corresponding checksum, you have a cached content saved. If yes, you can restore. If not, you'll have to go move on and do your regular activity. Now, identifying this input, depending on what you try to do, can be quite difficult. So there are 2 methods of doing it. One is that you identify your inputs manually. You just create a list of it. For example, if you're only concerned about RTL files from a certain directory, it's probably an easier way to just do it manually, like all files from a particular directory. But oftentimes it becomes more complicated since you start accessing from various different locations, often from networked file locations also. So you could automatically identify all input with some sort of tracing mechanism. Now you have to exclude all the files that are not relevant. For example, an EDA tool will easily access a lot of system files. It could also use some machine-related files that is really not relevant when you want to take a decision whether your design content changed or not. So you have to create that superset, then exclude the ones that you don't want. Or the other method was just the one that we just talked about. You create by including all the inputs that you want. In either way, over the long time, it really becomes difficult to create this and maintain this, because sometimes projects change, ownership changes, and content also keeps changing. So this becomes very difficult to maintain. Now, we are just talking about, there's an asterisk explanation. We are just talking about the very first run when you check out a repo for methods 1, A, B, and C. If you have to do subsequent runs and you want to see if you want to reuse the cached content, the checksum method that we just talked about can also be deployed for method 1 caching methods. Now let's talk a little bit details about the method 2B. Right? So we're talking about having a CI infrastructure. So CI infrastructure takes all the user changes, then it runs all the acceptance checks, and then the additional step we have added is that after running a tool, it prepares the cache as the tool runs finish. So typically we have more checks running after a particular tool that we want to cache runs. So this is generally hidden behind other checks, so we don't see any runtime hit. The next step is the CI infrastructure decides whether these changes are acceptable and should be part of the head of the repo. If no, then the entire submission is rejected. Whatever side business we did with the caching is also just discarded. If not, if the submission passes, then we create a unique tag for the new commit with the user's changes, and then copy the cached content using that tag. So we use the tag as the directory name. We copy those to our cache disk. Then we commit the changes, and this is regular CI activity. We publish the updates as a new head of the repo. So these are the two changes. Once you are running, prepare the cache, anything you need to do with the tool run results. And if it passes, you have a quick stage where you just copy whatever you prepared for caching using a unique tag. So unique tag is the identifier. On the restore side, this is at the user end. What we do is the user decides whether to use the cache or not. For example, if they're running validation, they didn't touch any of the RTL, they can easily decide that the RTL compilation elaboration can be reused. So if they're not reusing, they just go on as usual, no change in work model, they run their tools as they did before. If they want to use cached content, we have a small script that checks their current tag of the repo and then checks whether a matching cached content exists. If it does, then the retrieval is done automatically. It's a simple copy command, and anything that is needed to localize the content if necessary. Right? Then either the entire tool run is skipped, or some portion of the tool run is skipped because we are using the cached content. Right? So this is basically how method 2 works. This is the pseudocode. I won't go into too much of the details, but just to make a point that this is practically all that you need to code. And even in real implementation, it's less than 100 lines of code. So it's very simple. All we are doing is, first we are defining what we want to cache, what sections of your tools you want to cache. Then we are deciding if it's CI, then we are creating a user unique tag. We are copying from the user run area to the central cache disk. And if it's not CI, then it becomes vice versa, the reverse. Then if it's user run, then we check for cached content. If not, it's the same for both CI or user. If it's CI, then we do a pre-cache processing. Sometimes directories or file names require some changes, so those are done if as necessary. Then the content is copied from to directory, and then if it's a user, then you do some post-processing if necessary. Again, this might be necessary if you have some hard-coded paths, for example. Right. So this is the pseudocode, and with that, let me move on to the results section. So we have two pieces of results that we are presenting. This is this section basically works before we go into compilation and all. So the content is various types of code generation that you need to do before you start your simulation. And the target audience here was about a team of 20 people. So once we started using, we saw a steady use of a couple of checkouts every day for the time that we measured. We also did a fresh measurement recently, just before the presentation. So it's still continuing to use. So now to give it an idea of how big or small this usage is, once a validation engineer, for example, checks out a repo, they don't discard it immediately. They work on it for a while. So a couple of use case every day is pretty significant, which means they're using it quite regularly. And each user saves a couple of hours. Next, the result that we're showing is on simulation model building. This is generation of the binary executable, not the run. So by using the cached content, we were able to reduce the runtime somewhere from 70 to close to 60% in the runtime. We're showing from 3 different variations of a production design. One is where only the boot model is used. The other one is functional, and the third one is the entire design. So in each of these designs, we saw significant runtime reduction when we used the cached contents. That takes me to the conclusion slide. Caching or reusing the EDA tool run results can significantly improve tool runtimes while also reducing compute usage. We have seen this from our experience, and we have presented multiple ways to achieve this, particularly method 2B in this presentation. As a result of this, we see significant improvement in designer productivity because they don't have to wait for long tool runs, right? And eventually it turns into faster project turnaround time. So at the end, what I want the audience to leave with is a call for the EDA industry, because there is a significant untapped potential here for the EDA tools. The tools need to make sure that their run results is self-contained. It's portable, it's reusable, doesn't have hard-coded paths, etc. Tools should have a very quick way of evaluating how much of its input has actually changed and how much of the results from previous runs can be reused. Tools should also give us a way to reuse existing tool run results, not just from current work area, but also from shared work area, which helps with larger teams and large-scale designs. With that, I will conclude the presentation. One last point, thank you very much to Simha for his support in deploying this proposed method at Intel. With that, I think we are ready for questions and comments.
Thank you, Ashfaq. That was pretty good presentation. And well, I had a question for you. Actually, the first question from Pavan was also pretty close to my prepared question. How are you, when you say that design is not significantly changing, we wanted to know some more metrics on that. For example, I mean, you could have a one-line code change in your design that ripples through the entire design. So have you characterized these types of changes or created any types of guidelines to users to help work with this caching scheme? You're muted.
Right, thank you. So can you hear me?
Yes, now I can hear you.
Yes, it's a good question. So understanding the impact of your change, it can be tricky. It might, like you said, even if it's one line, it could have ripple effect. But the way you organize your tool run should be able to contain that impact. Like I gave an example of let's say your simulator compilation, right? Even if it changes one line, yes, functionally it could change a lot of stuff, but how you compile and how you elaborate your design, if that is structured, then much of the tool run result can be reused. So that's what we mean by like containing your changes of the design. Other examples could be you may have multiple IPs in your SoC, but right now you're focusing integrating only one IP. Right. So again, if you take the example of simulator, you don't have to recompile everything. Elaboration has to be redone, but if it's partitioned well, then even elaboration can save a lot of time. The same goes for any kind of static check or structural checks that you do on RTL design.
Okay. And the next question actually was my second question as well, about what kind of example EDA output would you call out that could be cached? So, and I was looking, have you kind of categorized all the different kinds of outputs?
Yeah, so right now we focused on RTL only. So we have some internal tools that do code generation. I'll leave those aside. But EDA vendors where we significantly use EDA tools, simulation model building is one big one. There are static checks when we do RTL linting or low power linting, CDC linting. Those tools also have significant cache usage.
Okay. And I think we have time for one more question. And that's how much, this is from David Lacey, how much cached history do you save? Is it a sliding window history? And then what's the storage capacity allocated to the cache data?
It is a sliding window, so it depends on how much resource you can afford. So with the test that we presented, we are using a 2 terabyte design, and that allows us to save about little more than a month, maybe a little less than 2 months worth of design. But it depends on how much you can afford and how much old data you actually want to use.
Okay, any other questions, anybody? If not, then thank you very much for your presentation. And a reminder for everyone to go to the voting tab and vote on the presentation.
Thank you.
Okay, and our next presentation, and I believe the speaker has not shown up, and that was Choi. And let's see, I guess we'll just run the presentation. And then any questions you can put in the conversations chat. And then we'll get those questions to the author. So I guess we can start that presentation now.
Hello everyone, I'm Choi. I'm working at Samsung Electronics as an engineer, and I mostly develop the system for design verification with machine learning techniques. Before we get started, let me ask you 2 questions. Have you ever struggled with repetitive debugging in a design verification process? Or have you ever been annoyed with the shortage of license or servers? In this presentation, I'm going to share you how our team has successfully reduced overall verification time with machine learning and systematic approach. As all of you know, the complexity and size of digital designs are getting immense. This graph shows that engineers' efforts and computing infrastructure cost for verification have increased so far. This trend will be accelerated with the increasing number of IoT devices, mobile devices, and automotive cars. From this trend, we noticed 2 problems. The first problem is described in this graph. The graph shows requests for a license in our company for a month. This horizontal line indicates the maximum capacity of a license with purple color. It shows that the number of requests for licenses are not uniform but concentrated on just a few days. In other words, resources are idle for some days, but very busy for the other days. In this situation, many verification engineers have to wait for a long time to get resources and simulate their test cases. What is worse, in such a limited resource capacity and fluctuated resource usage, verification engineers often debug the same errors repetitively from similar test cases throughout multiple projects. Even though engineers already reserved common and power-related bugs for the first and second test cases, he has to debug the same issues again for the third test case. While debugging the same errors, memory-related bugs are not revealed. Sometimes these kind of critical bugs are found in the later time of debugging process, and this problem can bring about the delay of the project schedule in the end. To help verification engineers suffering with these issues, we suggest 4 aspects as follows. First of all, let's make groups of test cases based on similarity and call them as clusters. Each cluster has similar test cases, and the result will be used to prevent repetitive debugging. Then prioritize test cases in each cluster and run them with higher priority. This process makes sure that these similar test cases could be launched first. For the remaining test cases in each cluster, our proposed system automatically runs them when resources are available. For example, at midnight, early in the morning, or weekends. Finally, all of these phases are optimized by distributed systems to make our proposed algorithm served in a timely manner. This is the overview of proposed algorithm flow. Our goal is to reduce time and cost of finding errors with minimum number of test cases. To achieve this goal, the proposed algorithm flow is composed of 3 phases. In data pre-processing phase, we first collect terabytes of log files generated at the end of simulation. Then collected test cases are clustered based on their similarity. Finally, test cases are prioritized to maximize resource utilization and minimize debugging time to find different kinds of errors. Before we look into data pre-processing phase in details, you might wonder why we choose log files as input data of machine learning algorithm. In fact, the easiest way to extract information about test cases is to use a test name. Test name contains intuitive clue about what behavior test case is intended to verify. As you can see, it's straightforward to figure out the similarities between test cases. However, as test name provides limited amount of information, it's hard to figure out accurate similarity between test cases. Also, it's difficult to guarantee that test names always correspond to the actual behaviors of test cases, because there is no standard naming rules. However, in log files, there are a lot of data associated with test cases. From log files, we could get not only test name, but also sequences, functions, and errors, which are actually composed and executed during the test. Furthermore, these data are reliable and correspond to the actual behaviors of test cases. With these big amounts of data, we could easily identify unrevealed similarities. As a matter of course, dealing with log files increases the operation time for additional processes. Even though these kind of effects, it's more advantageous to extract considered similarity of test cases by looking into log files. Besides, the pre-processing time shrinks on account of distributed system efficiently. Due to these advantages, we extract the data of interest in the log file and we are gonna call it as components. This phase is called data pre-processing phase. In this phase, duplicated components and any number or non-word characters are removed. Then preserved components are tokenized and transformed into vectors in the suitable form for machine learning model. For vectorized components, we applied time frequency and inverse documents frequency, which is known as TF-IDF. Time frequency refers to the number of times time appears in a document. When it comes to how common or rare a word in the entire dataset, the inverse document frequency of the word is also calculated. The vectorized input data will be transferred finally to machine learning model after reducing dimensionality. In the clustering phase, we applied k-means clustering, which is one of the most popular unsupervised machine learning algorithms. The goal of k-means clustering is to group similar data together and to discover underlying patterns. The process of k-means clustering is simple. First, after setting k value, k number of centroids are randomly selected. Then each point is assigned to the nearest centroid cluster. Once all points have been assigned, a new centroid is computed for each cluster. These steps are repeated until there are no changes to the elements of clusters. There are two reasons for applying k-means algorithm for clustering our data. As calculating new centroid of each cluster could be performed in parallel, we can maximize throughput in distributed systems. Moreover, k-means clustering can be extended to a weighted clustering algorithm, which can weight specific components based on engineers' domain knowledge or their inference. The details are well described in our paper. In k-means clustering algorithm, the performance highly depends on k value. To find optimal k value, each cluster is evaluated with elbow method and silhouette scores. Elbow method finds optimal k value until there is no remarkable improvement even with additional cost. Silhouette score indicates how clusters are well apart from each other and how similar the object is to its own cluster. We choose k value that maximizes silhouette score considering the slope in elbow method graph. In each cluster, our proposed algorithm prioritizes test cases in this phase. The purpose of this phase is to shorten the overall simulation time with the very least use of resources, by selecting test cases that can find different kinds of errors with the minimum number. Test cases with higher priority in each cluster are simulated first. Then what about the remaining test cases? They are automatically launched when resources are available. We believe this approach will maximize the resource utilization while finding out different kinds of errors in the earlier time of design verification process. For prioritization phase, we compared 4 different methods. Random method randomly samples a specific number of test cases from clusters. The farthest first selects the test cases in the order of the farthest distance from the centroid of each cluster. Closest first selects test cases from each cluster in the order of closest to them. Error count and runtime-wise method takes into account the number of errors in the test cases at runtime. This method is based on the hypothesis that when there are many types of error in the test case is more useful when extracting failure cases, and that the shorter the execution time of the test case, the faster the error can be found. The purpose of this phase is to sample representative test cases to find different errors as early as possible without running all test cases. Of 4 candidates, one method is selected based on how quickly a specific error detection rate was achieved. For each regression, the most efficient prioritization method will be automatically selected. To validate our proposed algorithm, 35,000 of log files are examined, and 4,500 components are extracted in the data pre-processing phase. This means that each of the 35,000 test cases is made up of combinations of some of the 4,500 components. At the clustering phase, we found that 18 is the optimal k-value for k-means clustering. The chart on the right side shows the distribution of k-means clusters with optimal k-value. Based on the clustering results, we compared 4 prioritization methods to find out which one is the most appropriate for our data and how it could reduce overall verification time and resource usage. In this graph, the gray line shows the conventional verification progress without any clustering and prioritization methods. The conventional method takes the longest time to find 90% of errors. However, other methods with our proposed algorithm show a few days faster time to reach the target ratio. Of all the prioritization methods in our proposed system, the farthest first method shows the best performance in achieving the goal. This result was quite surprising to our team, as we expected the error count and runtime-aware algorithm to perform best of all algorithms. Our proposed algorithm can reduce the overall verification time by 9 days compared to the conventional time-consuming approach. Results from this data indicates that errors can be found as quickly as possible when selecting test cases from the farthest distance from the centroid. Our proposed method not only shortens the overall verification time, but also reduces the number of test cases to be executed. This means that We can achieve our goal with minimal resources, such as licenses and servers. In our result, when the number of test cases in the conventional approach was set to 100, our proposed algorithm showed fewer test cases to achieve the same goal. Of all methods, the farthest first method used only 76% of test cases. In these experiments, we expected error count and runtime-aware algorithm might show the best performance, but it was not. We found that the lack of historical data could be the cause of the lower performance of the algorithm. In our empirical view, the performance of the algorithm will be better when it accumulates more historical data from multiple verification cycles. In conclusion, we proposed a novel log analysis method with test clustering in distributed systems. We first clustered test cases based on their simulation logs and prioritized them in each cluster to minimize verification time to detect different kinds of errors and to maximize resource utilization. We also propose robust and scalable system architecture, handling terabytes of data for practical use in design verification industry. To validate the proposed algorithm and systems, hundreds of thousands of test cases were used as datasets. According to our experiments, the proposed system remarkably reduced overall verification time and wasted resources, and efficiently automated design verification workflow with machine learning and distributed systems. This indicates that the algorithm and system enable verification engineers to help to reduce repetitive and tedious debugging tasks and to focus on finding different or critical errors in digital design. Even if the proposed algorithm showed improvements in debugging process, there are still many challenges. First, this paper uses only k-means clustering algorithm as it is suitable for our datasets. Other clustering method can be used in the future algorithm. Also, the algorithm is based on a specific version of the project, but it can be improved by considering overall history of projects. Such challenges are under consideration in our future works. Thanks for listening to the presentation. If you have any questions, please contact by email.
Okay, thank you very much. As we mentioned before, Jin is not available for questions, so you'll have to either send her via email or you can use the conference tab to get questions back to her. And a reminder, please go to the voting tab to vote for the paper and presentation. And also the next presentation, machine learning based verification planning methodology using design and verification data by Hanna Yang, is also a colleague of Jin, and she is also not available. So we're just going to run that presentation and go ahead.
Hi, I'm Hanna from Samsung, and I'm really happy to introduce our study to you. My major role is making automation system for design and verification field. In particular, since I belong to the verification team, I think a lot about how an effective verification process can be carried out. Well, as you can see, the subject of this study is machine learning-based verification planning methodology using design and verification data. And it is the result of this thought. Let's move on to the next page and take a look at how Seonhee and I develop our thought. think this picture is quite familiar to you. What I'm trying to say now is a story which is maybe you already know, and you probably heard of it. As you already know, the process of developing a single SoC product requires hundreds of components and hundreds of people or more, which must be well organized in optimal condition and communicate well with each other. And we would be so happy if something existed as a standardized template for the SoC development process. But as you know, traditional skills and experiences are becoming more and more difficult to educate and share as quickly as they have been before. Because the component types required by SoC products continue to change or increase. And even the people in charge of the SoC design or verification also continue to change. So, we have to communicate through data. Each component of the SoC product is connected in a very complex hierarchical structure. So, between each component and the design or verification owner who is responsible for it should communicate with the design component, managed by the same architecture and the standardized interface. And the tool for the communicate must be data. As I mentioned earlier, each component of the SoC product and the design or verification owner should communicate with the standardized data. In particular, design and verification should be more closely communicated with the same data. But in the real world, it's not like that. Look at the picture here. There are 5 apples, each on the left and right side. Do you think 2 pictures are the same? The apples on both sides have different positions and colors. This situation is similar to the reality of design and verification. Design and verification are separated into different organizations and have their own component management structure and interface within each of them. But design and verification make the same product. Why don't we think about the process of development SoC products with time information or development stage? This is a very brief schematic diagram of the developing SoC process in the Samsung. SoC product development process from specification to IP development, block development, and top-level development. And numerous design revisions occur during the development process with each development stage. The verification team should complete perform verification as soon as possible for each design revision to detect bugs early and achieve product completeness quickly. Design size is getting bigger and simulation resource is limited. How can you do higher quality verification fast? This clever idea is very simple. It is focused on the changes between 2 design revisions. If there is a new change in some part of the design compared to the previous version, there is a high possibility that a bug will occur in the part or in the part linked to that part. Therefore, if we perform only the part of the verification component or do the part first when performing the verification, our chance to find bugs will be increased efficiently and quickly. But there are real-world barriers here as well. As I mentioned earlier, design and verification work with different management structures and interfaces. So it is not easy to find exactly one-on-one matching locations where the design changes belong to the verification plan and test scenario. changes in the design inevitably lead to changes in the verification plan or test code. But the relationship between design components and verification components is not determined clearly. So it is difficult for verification owner to infer the correlation between design components and verification components. So we introduced the concept of data orchestration using machine learning and used it to find a clear connection between two sides and apply it on the verification process for fast and high quality verification. Data orchestration automates processes related to managing data, such as bringing data together from multiple sources, combining it, and preparing it for the data analysis. We selected 5 types of data for data orchestration. They are design component information, change information for each design revision, design stage such as IP, blog, top-level design information, verification component information, and verification test result for each design revision. As I mentioned in slide 5, these data are being collected from automated systems such as Debug and DDA, which we developed ourselves. So we were able to use this system for data collection. And these systems were explained in paper, which is submitted to DVCon U.S. 2020. In general, there have been many correlation studies between SOC verification components and verification results. But this research that encompasses design data and verification data, which are generated at each stage of development, is the first to be attempted at least in our company. Among the 5 data to be analyzed for data orchestration, the verification component is close to a natural language, freely described by the verification owners with just few rules. So, pre-processing for data analysis must be preceded. We first prioritized some verification components in the frequency of each word, and then hash mapped them, and then remove unstructured strings such as test conditions. And after applying some statistical libraries provided by Python, the information of verification component was finally set to vector form. With the data of vector form in the previous slide, we used machine learning to categorize the verification components in our paper named class and analyzed it using a total of 7 different scales of SOC projects. We found that the optimal number of classes to classify verification components is 52 using statistical techniques. And we classified the verification component using a machine learning tool called K-means. This picture shows the actual verification component of the class with the label 26. The 52 verification components were used as learning data for the machine learning model. This slide is a simple schematic of deep learning model that we applied. We used 4 hidden layers and 2 dropouts, and ReLU was used as an activator and AdamW was used as an optimizer. Recently, these are known to perform best in the classification model of machine learning. And in fact, when we tested the model performance of machine learning with various types of activator and optimizer, these were the best in our data. This slide shows the result of analyzing the correlation of all the data to be analyzed. As I mentioned earlier, design components, design changes, and design stages were obtained from the Design Data Analytics System. We called it NTDA. We developed ourselves. And verification components were obtained through machine learning in the previous flow. In addition, the verification test results from each design stage were obtained from the verification regression system. It was also developed by us. As a result of analyzing the correlation of all 5 items of data, it was confirmed that each specific design component is correlated with the failure of the verification component and design changes sensitively. In particular, in case of changes in port bus has a negative correlation with failure, so they have stabilized the design. And in case of changes in component interconnection, have a positive correlation with failure, thereby increasing the instability of design. In the figure on the left, the string marked with spec on the y-axis is the design component. And the number shown on the x-axis is the verification component classified by machine learning. And the class order table for the verification schedule on the right side is the result of the ordering the verification regression schedule by scoring the verification component and test result for each design stage. This slide shows you an experimental result of the process described ahead. This result was tested in VR3, the third stage of the verification stage. In fact, verification is most active at this stage, so the results are best in VR3. And this line chart shows the trend to find the entire failure in the optimization situation that is reordered as a result of machine learning and actual situation. The orange line is the optimized result, and the blue line represents the real result. As you can see, the slope of the orange line is steeper than blue line. And when you find 70% of failure, it takes 10 days in real. But in optimized situation, it takes only 6 days. Therefore, as a result, TAT to find 70% of failure in VR3 has been reduced by 40%. This is the last one. At this slide, I'll tell you about conclusion. Our goal is shortening TAT and improving completeness on verification with short TAT. So, we think that the failure pattern can be generated at each design stage, and it might be similar for each project. To find the failure pattern, we selected some data such as design and verification components, and simulation results with each verification stage, and then analyzed it. Finally, we made a verification plan by using machine learning, which is detecting failure earlier than previous process. We think there's still a lot left to enhance the result. Actually, data analysis requires a huge amount of data, but we lost a lot of data every day. So the most important thing is preserving more data. And we are going to try to maximizing machine learning model performance. That's all I want to tell you about our research. Please refer the paper for more detail, and feel free to contact us if you have any questions. Thank you.
Okay, thank you, Hanna. And as I said at the beginning, she was not able to attend. I think she's in Korea where it's like 3 a.m. or 4 a.m. And a reminder to vote on the paper, or go read the paper and vote on it. And with that, we'll go to our next presenter. Robert, are you here, Robert? I think you're here. Or he was here, I'm sure.
Yes, I'm here.
Good, great. Robert is an engineer at Samsung. He got his degree in engineering at the University of Texas in 2011, and he says he's been working on continuous integration for 10 years. So that pretty much means his entire career has been focused on this. So with that, we'll get the presentation going. Thanks.
Hello, my name is Robert Strong, and today we're going to be reviewing how we improved our continuous integration flow using a scheduler. A brief overview of what we're going to cover today. We're going to go over the problem statement for our organization and what we had previously implemented to resolve it, kind of the issues of why we needed to improve and the new concept we came up with to fix them. We're going to review how we put those in place, what we learned along the way, the data that we can measure of the effects of this new flow, and then we're going to discuss future improvements and open up the floor to any questions. Our organization's problem statement was that we had a large number of user change sets that we needed to test and get into the repo. Our test time was about 2 hours. So with a large number of change sets, combining them, filtering out failing cases, and accepting passing cases started to result in long turnaround times. This was only exacerbated during milestones that each submission was important. Users were closely paying attention to them, and the delays became problematic. Our previous flow, we had less user submissions and a shorter test time when it was originally designed. And we also had a smaller batch system, so it was designed to conserve resources. Because of this, it was implemented serially, where it would test change sets one at a time, trying to figure out what was accepted, what could be accepted, and what couldn't. It also was stage-based in that it would run these tests and it could take action, but rather it would wait for multiple results to come in, look at them all, and then decide what to do. Originally, we tried to incrementally improve this to resolve our issues, but we came to the conclusion we needed to just start from scratch. These are some examples of some of the issues we ran into. Originally, the flow was optimistic that users were all submitting passing change sets, which that's not really the case. So in this example, we have A plus B, and A plus C, A plus B plus C. And after A plus B passed and A plus B plus C failed, we know we should be able to eliminate C and then start with the next ones. However, this one needed to run C in isolation before it would eliminate it. Also, as soon as A plus B passes, we should be able to kick off D and then D plus E as soon as they arrive. This one waited for each of these reggers to finish before it kicked off the next batch of reggers. We had an incremental change where we started testing change sets individually before we combined them to try to eliminate these failing change sets that could cause variable turnaround times and disruptions. But this guaranteed that best case, your turnaround time would be 2 times your test time. So it'd be 4 hours. And we were running into issues here. What we came to the conclusion was that if we want to run multiple test cases, always react to events, and drive down our turnaround time for passing and failing test cases, we were working towards a scheduler that every time a new submission came in from a user, it needed to react, decide what to do, and launch test cases. And then every time a test case finished, we needed to react and decide, do we pass? Do we fail? Do we create more test cases? Do we kill test cases? But always take action when something changes. Either a user submits or we receive information from a test case. And the goal of all this was that our turnaround time would be equal to our test time, no matter the state of the queue. You can have a high fail rate, a low fail rate, a large amount of turn-ins, a low amount of turn-ins, and you should always have a turnaround time that is equal to your test time for passing. And for failing, it should always be less than your test time. Here's a very simple visualization of this concept, where we have 3 submissions, A, B, and C. We know ahead of time, well, we don't really know, but A would be passing, C is passing, and then B is failing. And it shows how the scheduler accepts A and C both within test time and then removes B from consideration in less than the test time. And it did have to launch these extra test cases that ended up not being used, which we will address this later because it does seem wasteful. So in our steps to implement this, we started with an individual scheduler. Its job is separate from the scheduler that creates test cases of multiple change sets. It has the special job of creating an immutable copy. And we implemented this one through local scripts of our own. Part of it was security reasons and kind of flow reasons I can't go into, but it would query for new user submissions, create immutable copies, launch a test case of the user change running individually, and then it would ping our combined scheduler to go launch more test cases. Our combined scheduler we implemented through Jenkins. And every time it was pinged, it would wake up, grab the state of the queue, decide what new test cases it needed to launch, prep the workspaces for them, and then it would create prop files for each one, and then launch the jobs and exit. This was designed to be as lightweight as possible. These jobs run in about 1 minute. And all they're doing is very basic logic, deciding what needs to go and then launching it off. The one note here is that originally we wanted this to be as absolute lightweight as possible. And if we were to do that, we would trust the merging to be done in the test cases. However, we ran into issues doing this in that if you launch off multiple test cases with change sets that are going to have merge issues, you start to get lots of conflicts coming back to your processor which was just harder to sort out and weed out what to fail and what not to fail. So we actually found it easier to create the merges of change sets that we're going to run in each test case in our scheduler. This added a little bit of weight and time to our scheduler, but it's still relatively insignificant. And we found the very easy way to implement this was through the Jenkins prop system. That Jenkins has a plugin to launch jobs for every prop file. And so all the scheduler needs to do is, if it decides we need to run 5 test cases, it just needs to create those 5 prop files, put the relevant information in them, and then send them off to the races. This is a quick visual of the details of how we implemented those prop files. It also kind of reflects how we know the state of the flow every time the scheduler wakes up. When we first conceived this, we thought it was going to be complicated to try to always make sure we've covered all the bases, but we found it was relatively simple. We do most of our state tracking just with files. We have a directory and it has all the .prop files of active test cases. And anytime you want to see the state of what is running, you just need to go look at these prop files, and that's it. We have a simple database that really only tracks if candidates have passed or failed, and small amounts of metadata like retry and priority. But outside of that, most of the flow is just tracked through our file system. And then all these prop files, after they're completed, we move to an archive directory. That way we can always see a replay of how our test cases were run. And it makes our active directory very easy to parse. Each one of these prop files has all of its relevant information contained in it. With a quick example. And then this is how we implemented our test cases. So Jenkins kicks off a job for each one of these per prop file. And all it really does is run our test case. It just lands on the workspace that the scheduler prepared, runs our test case, and then returns a yes or no. And then our scheduler and our post processor will figure out the rest. And then the way this works is if it completes a pass or a fail, it calls our processor. And we call this processor through another actual Jenkins job. And we do this so that we can make it serial. We don't want our processor running 5 jobs in parallel, because they will start stepping on the toes of each other. They will, while they're failing and passing and submitting jobs, we want that to be one at a time, just to make things simple for us. Which I forgot to mention, the same does apply to our scheduler. Our scheduler only runs one at a time. However, we do run our post-processor script in parallel for aborted jobs. We run test cases, and when we deem them no longer relevant, we abort them through the flow. And if you've been killed, the post-processor doesn't really care about any of your data. All you really need to do is clean up after yourself. So we have this other hook to always call the post-processor, even on an aborted Jenkins job, which this is important because we rely heavily on using the Jenkins API to call aborts. Okay, and then moving on to our post-processor, I mentioned this, that it has 2 modes. One is when it's completed, it looks at the change sets that have completed in that test case and then decides as best as it can which ones to remove from considerations, which ones to push back to our source control. And then it goes and looks of, okay, what test cases are no longer relevant. And I use the word subset and superset here because subset is for passing. If you have a test case of A, B, C, and D that is passed, you no longer need to worry about A, B, and C. So if that test case landed on a slow batch machine and it's still running, you can go tell it, don't bother, stop running and just clean up after yourself. The other one, and the subset does happen, but it is less common. The superset is more common, that if you fail, we know that any other test case that contains that combination of change sets can be killed. So the easy example would be if B fails, we know we can kill A plus B, A plus B plus C, B plus C, B plus D, anything that contains B. And that also applies to, if B plus C fails, we go and kill B plus C plus D. So it goes and figures that out, which the logic to do that is very, very simple through our prop system. In reality, all it's doing is running greps through all of our active.prop files and finding which ones match. And then the prop files contain the Jenkins job ID. So if it finds a match and it knows it can kill you, it runs a quick command through the Jenkins API to kill that current test case job. And then for completed and aborted mode, but these are only aborted run mode only runs these three steps. We update our file system to correctly reflect the state of all of our test cases. We recycle our workspace and we notify users. So whenever we call this Jenkins API, we know that all these aborted jobs will take care of themselves. While we were implementing this, we came across some best practices that helped the flow dramatically. And the number one thing we're trying to do is reduce the cost to run a test case, because this flow relies on running a lot of test cases, sometimes excessive amounts of test cases. And so the more you can minimize the cost of a test case, the more you can ramp it up to the point that we are trying to make it guilt-free to launch and kill a test case. If launching a test case has a 10-minute overhead and it strains your resources, you're going to run into problems with this flow. So we tried to eliminate that as much as possible. And some of the things we implemented was to exit immediately on fails. And that comes down to individual test level to the test suite level, that you want individual tests as soon as they know they're going to fail to exit out. And then the test suite, as soon as it sees that that individual test has failed, to exit out. And then the test case, as soon as it sees the test suite has failed, to exit out. Propagate exits or fails from the entire flow up as quickly as possible. This might be just our organization, but we ran into a lot of false fails due to external dependencies. Of users would submit a pointer to an outside local work area, and then that pointer was a ticking time bomb of If they decide one day to change a file, it could bring down our whole system. And that speaks to the idea of this flow really works and shines when you can count on your exit codes. If you're experiencing a lot of false fails, it's going to be problematic because it really tries to launch and destroy test cases as quickly as possible. And if it's getting false exit statuses, it's going to make a mess. Which we have techniques to minimize false fails in our organization. Some of them are at the individual batch level of when jobs exit, we try to catch strange exit codes and immediately requeue them. But then we also have it at the higher level of when an entire test case exits, we run some quick parsing. We look through a couple logs and we try to find, okay, do we really believe this is valid? And if it's not valid, we can at least say, don't take drastic action. Don't go kill supersets of this fail. Let's wait and see, which can be really useful. And then recycling workspaces was important to us because for us, creating and destroying workspaces for all of these test cases did become a large cost on our resources. So we really emphasized that our flow was not for user debugging. It did tar and catch fails and send them off to users to debug, but we're only going to exit on the first fail. If you're submitting something with 50 fails, you need to recreate them locally because you are costing all the other engineers time trying to debug it in our flow, and that's not really the purpose of it. This is a review of how these changes improved our turnaround times, which those turnaround time was the end all to be all of our goals here. Some of these changes were done over time. They were not all rolled out immediately. So it was a gradual process through a project, which this graph reflects that we tried to clean up random fails and enforce code checking for external dependencies before rolling out the scheduler. But we do see that when we rolled out the scheduler, we saw a dramatic drop in our average and median turnaround time for submissions. Previously, the times were fluctuating between 4 hours to up to 10 hours with large swings weekly. And then once we implemented it in work week 23 of 2021, we saw a drop to 2 hours pretty consistently in our median. Our average did see some variability, but that was due to external factors out of our control. Sometimes there's network issues and issues that we cannot account for. But the median does a good job of reflecting that when our environment is healthy, the flow does a good job producing results. And in addition to this, I've included the submission count, where in work week 23 was when we rolled this out. And that was one of our highest submission counts for that week, in that we had 225 change sets go into the repo, and it was producing consistent results around 2 hours. Future improvements, there are quite a few. This flow was created with the intention of making it work. It was not created with the intention of having everything be perfect. And so there are parts of it that are relics of previous flows and imperfect implementations. The first is how we talk to our batch system. And there's two large points here. The first is that when we are killing jobs because we believe they're no longer relevant, if the post processor can easily query our batch system and see the state of our test case, or our test suite, it could make better decisions. And the example I would use for that is that if we are running A and A plus B, if A fails on some test, before the post processor takes drastic action, it can go and ask A plus B, hey, have you passed that test? And if it has passed that test, we would know that A is a false failure, and we'd have positive confirmation of that. Or if A plus B hasn't passed the test yet, but it says, yeah, I'm 2 minutes away from finishing, it can say, it's probably worthwhile to just let it run. We don't need to kill it. We don't need to be drastic. So it can make better decisions if it's actually looking inside our test suite, where right now it mostly treats our test suite as a black box, yes or no of have you returned an answer or not. The other improvement that we can make through our batch system is that right now we have implemented a large deal of this through Jenkins jobs just out of ease of use. But in reality, our Jenkins jobs are a glorified batch system that we could implement these hooks and these jobs calling each other and these dependencies through any batch system. It doesn't necessarily have to be through Jenkins, and removing that dependency could open up some more flexibility in the future. However, right now it's working very stable for us. So that's not an extremely pressing issue. The next would be to combine our schedulers. If you noticed before, I mentioned that we have an individual scheduler for change sets and then a combined scheduler for change sets where we have more than one. This distinction isn't really needed. It's kind of arbitrary. The only reason we have the split is because we needed the individual one to create an immutable copy. But we could easily create this with a pre-hook before our scheduler runs. The next thing is a dynamic scheduler that in practice, we don't always need to run every single possible combination of test cases. In the example I gave, we ran A plus B, A plus B plus C, B plus C, A plus C, B, C. I don't even know if I hit them all, but that extrapolates out to 2 to the power of n minus 1, where n is the number of test cases, which for 3, it's no problem. We can run 7 test cases. Once you start hitting 4 or 5, it becomes a lot. Part of the great part about the flow, though, is that if it does a really good job of clearing the queue as quickly as possible to try to keep those numbers low. However, it's not feasible to run every possible test case. So the flow does have to make some some considerations of how many test cases it really launches. Currently, I do that somewhat manually, but the flow could be smarter and tweak itself based on what's available and what's the appropriate choice to try to determine how many test cases it should be launching at once. This is also very project dependent, depending on how much time it takes, what your pass rate is, how costly it is. So lots of different decisions can be made there. But I believe that you should be able to make those decisions just with a couple settings or a knob. And right now that's not available. We would also like to push for partial testing in that we run the full test suite no matter what your change sets are. If you just check in a README that has absolutely no chance of breaking any of our tests, our flow does not know that. And being able to move those user submissions through our queue quickly helps free up resources to run more important test cases. The last part is how we pass data from scheduler to the test cases to the processor. Right now, we use the .prop files, and they work pretty well. But it's a very simple system based on greps and looping through files. But if we were to migrate this to be a JSON or something better, we could have something a little bit more complex. We could make it easier to query and interact with all of the different test cases. But that's brainstorming for the future. That is all that we are covering today. So I leave the floor open for questions. I do realize some of the things I have not covered here today are, do we face major issues? What reliability issues do we hit with the flow? What does our admin interface look like? If sometimes you need to do some hand holding in a queue, and how do we do that? So there's still a lot of information to cover. Thank you for your time.
Okay, thank you, Robert, for giving us a deep insight into some of the tribal knowledge that goes on with the continuous integration system. I see that you've been answering a bunch of questions in the chat, but if there are any that you want to express just by speaking, we could do that now. Trying to think of one was from Ravi Ram about a time limit. Maybe you have already answered this.
Yeah, mostly we control the time limit by auditing anytime somebody tries to edit the files that have our test list in them. And then what Daniel mentioned of the timeout plugin, we do have that, but that's more to catch infrastructure issues of, rogue machine is running forever or something like that. Not to catch time increases, because our runs have a little bit of variability to them. They could take somewhere between an hour and a half to 2 hours. So we can't just set it at 2 hours and 1 minute for the timeout and then block everybody. It just wouldn't work.
Okay. Oh, and I also wanted to mention to people that joined on the half hour that we had started early because we were missing 2 presenters. So that's probably why we finished ahead of schedule here, but that gives us a lot more time for questions here. And we've got another one from Ashfaq on compute resources. How did compute resources requirement increase now that you have many more test cases, given you also have some optimization? Not sure.
Right now, we do not have great numbers of the before and after of what our total compute was. That is also one of our initiatives, is kind of, we've been collecting a lot more data to go along with the flow so that we can measure what these changes are really doing. But we didn't have that in place when the flow first started. So we don't have a kind of a before metric to compare against. I can say that total compute time relative to our regressions, it's very small.
Okay. I know that you didn't go into any specifics about test selection. There have been a lot of other papers. In fact, one of the earlier sessions about trying to select the right set of tests for a particular set of changes. But have this process, have you fed back any type of test writing guidelines to help this process along?
Not yet. The big part of this was basically treating our test list as a black box and just saying, if that's immutable, what's the shortest we can get our turnaround times? And we've hit that wall. And so now we're starting to try to lean more on how can we change that test list. So we are starting to look through why do we run things, what's the consequence of if it fails, is it worth the runtime for every change set going in? But that is a work in progress.
And what about sort of the pre-check-in tests that, so you're not involved with that at all? Or?
Our pre-check-in tests are not, they're more sanity checks from our end of just making sure you dot your T's and cross your I's. You're not editing files you shouldn't be. They're more management test rather than validation test.
Okay. Are there any other questions? Some comments about wall clock time. Got a couple, somebody else answered that for you.
Yes, yeah.
I think I don't see anything else. Oh, have you tried Jenkins pipeline jobs?
We looked at it. I guess my opinion was that Jenkins pipeline jobs is good for the serial steps, but at least when we looked at it, it didn't seem like it helped us run lots of things in parallel. It didn't seem like it made that part of our flow easier for us. But it has been a while since we looked at it.
There are a small number of things that you can do with Jenkins pipeline jobs that you cannot do with freestyle. In particular, if you run a pipeline job and you use the pipeline script to trigger a downstream pipeline job, but then any changes you make to environment variables in that child's job will get returned to the parent when that job finishes running. So you can use that for some for returning results from a triggered job back to the upstream.
Okay, yeah, and that's our flow does work around that. We create breadcrumbs that pass between the different stages so that they know everything that went on. So yeah, that environment variable could be valuable.
But how do you manage the configuration of all of these jobs? It seems like you have many.
Could you say that one more time?
It seems like you have a great number of Jenkins jobs. How do you manage the configuration of all of them?
Because they're freestyle jobs, most of them, there's not too much complexity in the actual Jenkins end of things. The Jenkins end of things just points to scripts that we control. Mm-hmm. And then, when we roll out changes to those scripts, it applies to everything that points to them. So I guess configuration is code outside of Jenkins.
Okay, we have a question from Forrest Chan, do you snapshot, save, restore, and system Verilog dynamic load in your regression setup? So sort of some optimization questions.
I'm not familiar with snapshot, save, restore.
Yeah, I think that's sort of trying to get more common parts of tests out of the way and get more tests throughput. That's probably a different topic, I think.
And those are the type of things that I'm not an expert in, but we would love to have more and more of that. Anything that can speed it up would be great.
Okay, are there any more questions? Then if not, well, you can always continue the conversation in the conversations tab or send an email to the author. I'd like to thank you again, Robert, for your presentation, and a reminder to everybody to please go to the voting tab and vote for the paper and the presentation. And with that, we'll close this session. Thank you all for attending, and we'll see you at the next panel, which is coming up at noon. Thank you.